Hello and welcome to our very first hydrosphere lecture. So we're actually going to start doing some notes today. For those of you who I have forgotten to give notebooks, I expect you to still hopefully watch this lecture so that you know what you're doing. You're going to identify two things that you learned, and then I will give you the notes on Monday. But for everybody else, we should be using our notebook right now. We're going to do two sets of notes today, but let's get started with, as always, our vocabulary words. So here those are for you. If you will pause the video, go back. If you will pause the video so that you can grab these words, copy them down into your notebook, and then we have a fourth one on another slide. Okay, so hopefully you've copied down these vocab words. Let's see if I can shoot this for you, and it looks like I can't, but this is evaporation, that word down here. And then here's our last vocab word, pause it, and then we will move on. Our bell ringer is a video, so you will just skip your bell ringer section today if you're watching this pre-recorded lecture. And then we will jump right, we're not going to read the lecture either, we did that yesterday. We watched a video. So yesterday you watched a video that described for you the water cycle. So it went from, usually we start in the ocean, so a water molecule in the ocean, and then it can actually go all kinds of different ways. But in the case of our video, it went up into the sky, and it's water vapor, it changed from liquid to the gas. And then eventually it condensed or became liquid again and gathered around dust particles with other water molecules and actually formed a cloud until eventually there became too many and it got too heavy, and then those water molecules fell to the ground in the form of water as rain if it was cool enough, or solid as ice, or sorry, water if it was warm enough, solid as, or ice if it was cold enough, wherever it fell. And then where it fell depended on where the molecule went. It could have gone into runoff and become a stream or eventually a river. It could have landed on a plant and been taken in. It could have landed in the ground and soaked into the ground, only to be taken up by the plant and evaporated up into the sky through transpiration. Again, it could have gone anywhere, right? It could have been frozen and put into a snowbank. It could have been frozen and put into a glacier, and we won't move again for a long, long time, right? It just kind of depends, but eventually, hopefully, they all make their way back to the ocean where the cycle can begin again. You also listened to me read your story of Walter and his journey through the Catskills, which is a region in New York, which eventually he led out of the Hudson River, where I learned there are, in the Hudson River, there are seahorses, which was so interesting to learn. But that was really cool just to see the way that he traveled. Okay. But today we are actually going to do some notes. Our page looks like we are going to be doing both this page, talks about aquifers, and this page, which talks about wells. So we're doing 2 for 1. It's a special on notes today. We're starting with groundwater. So groundwater is the water that lands on the surface, often stored in saturated pores of solid or soil or rocks. Okay, so one of the things that we need to do is talk about the difference between surface water and groundwater. Groundwater, as you can imagine, is underneath and in the ground. Surface water, if you can imagine, is the water that you can see on top of the earth. So in rivers, streams, runoff, puddles, whatever you think, the water that we can actually see as it goes down into the rocks and the soil becomes groundwater. So it's under the surface of the land. If you look at our little diagram right here, this stream would be an example of surface water. So would all this runoff right here from the cows and the factories, in the cities and the factories. And then as the water goes down into the soil, we actually call that groundwater. Wonderful. Aquifer, something we are going to be studying in depth, and I'm very excited. We're going to be doing a lab on Monday when you come back, hopefully. If you are in Thursday, Friday, you'll have to tune in electronically to watch this lab. But we're talking about aquifers, so they are the permeable rock layers or sediments that transmit groundwater freely. They're an important and super vital part of our well water. So this is actually where we get most of our water from. We don't get it from lakes and streams and rivers. We get it, in Wilmington, you get it from the Cape Fear. But for the most part, if you live somewhere, you get it from an underground aquifer or well. So typically when you think of an aquifer, you might think of an underground cavern with a river or lake. And while those are true and those are out there, an aquifer really is just the space between rocks where the water can sit. So it's not necessarily this cavern right here as it looks in the diagram. It is actually just water that kind of goes in between the rocks because it's liquid and it can do that, and is there, right? Porosities is something that we need to talk about when we're talking about aquifers. This is the percent of total volume of rock or sediment that consists of pore spaces. When we sort rocks, we can sort them into porous or non-porous. Something with high porosity will allow lots of water to flow through. If you look at that diagram right there, if you can imagine, there's lots of space in between the rocks or whatever it is. So we have lots of room for water flow. Low porosity, we would have little room for water flow and not so much space in between the rocks, right? Some things that can increase porosity or lower porosity is the sorting. So if you have lots of different shapes, if you think of it as a puzzle, if you have different shapes of rocks, they can fit in nice and tightly, right? The little rocks will tuck in between the big rocks and make it harder for water to flow through. If you have all of the same size of rock, though, you will generally have a higher porosity, though it should be noted that the smaller the rock is, the more likely it is to have a low porosity. So that's something that's pretty exciting that maybe we'll study one day. Permeability. This is the material's ability to transmit fluids through interconnected pore spaces. So groundwater moves more slowly when the pore spaces are smaller. Duh. If we're thinking about a hose, right? If you think of a regular garden hose versus a fireman's hose, the fireman's hose has a bigger opening, therefore more water is going to flow more quickly out of the space. If you have a small little garden hose, or even think of a straw, the water is going to flow not as quickly and in a less volume out of a straw than a fireman's water hose. For example, fine clay is impermeable because its pore spaces are so small that water can't even move through it. So if I have clay, my water will sit on top of it and not go through. But if I have something like sand, which has a much larger particle, the water will flow through the spaces in between the sand particles and gather on the bottom. We also have something called the zone of aeration. So this is the region between the Earth's surface and the water table. The water table is the level below which the ground is saturated with water. A high water table during periods of heavy rain or rapid snow melt can lead to flooding. Since the ground is already saturated, full of water, no more can infiltrate the ground, which leads to flooding, right? That makes sense. If I have if my bucket is full and I try to put more water in it, the water is going to overflow. It's the same with the water table, but this is happening underground. So your water table levels can rise or can increase or decrease. But once a water table reaches a certain point, no more water will be able to saturate the ground, and it will cause flooding or puddles. If we have a small zone of aeration, that means that there's very little ground in between the water table, the level where it's saturated, and the surface of the earth. If we have a large zone of aeration, that means we have a very large amount of soil or rock material in between the Earth's surface and the water table, where the level of the water, or the level at which the ground is saturated with water. Zone of saturation is an area where water fills all the open spaces in the sediment and rock. Groundwater is within this zone. So when we are talking about aquifers, they are within the zone of saturation, which is where the water fills all the open spaces in the sediment or rock. if you will look at this wonderful, beautiful diagram that we do have. It looks like this lecture is going to be separated into 2 videos, which is fine. Here is our diagram. We've got our surface layer. Let's move me. We have our surface layer. We have the soil underneath. We have the zone of aeration, and we have the zone of saturation. So our water table, like we defined in the notes before, is the level at which the zone of saturation and the zone of aeration meet. So where we are completely saturated with water, so there is water completely saturated in the soil right here. It is not just a thing of water. There is soil particles mixed in here. The water is just in between the soil particles. That is the zone of saturation. At the very top of it, we call the water table. If we were to get more rain, water would flow down in through here and join the rest of the water molecules, and maybe the water table would rise. If we were to get less rain, or if we drilled a pump down in here and started taking the water away, the water table would decrease. Okay? So again, if you imagine it's raining, imagine my mouse is a water molecule, a Walter if you will. It's raining, my water molecule lands right here. It goes in through the soil. It keeps going, it keeps going, it keeps going because it can. Imagine it dodging around soil particles and rocks and dodging and weaving and going through and finding the little spaces and moving still, moving still, moving still until finally it reaches the point at which there are no more spaces for it to go through because the spaces are already filled with water molecules, and it stops right there, and where it stops is the water table. Very good. So to review some of the things we learned, because we're going to separate this lecture into 2 videos, we learned that an aquifer is an underground layer of sediments that transmit groundwater freely. So it is water in between sediments or pieces of rocks. We learned that porosity is the % total volume of rock or sediment that consists of movable space. We learned that some things that decrease porosity, making it harder for things to flow through, are sorting or mixing. So the more I mix my soil particles, the more likely I am that to decrease that porosity. We also learned that the bigger the soil particle, the more likely we are to have a higher porosity or allow more water to flow more freely through the open spaces. We also learned about permeability, which is the material's ability to transmit fluid or gases through its surface. We learned that fine clay is impermeable, which means that you are not able to pass water or air through clay. And we also learned the difference between the zone of aeration and the zone of saturation and the surface of the earth. So if it's the surface of the earth, the area between where the water table is and the surface of the earth is the zone of aeration. We learned the water table can rise or fall depending on weather conditions and how much water is being pumped out of it. And we also learned that the zone of saturation is where the ground is completely saturated or completely full of water molecules. It cannot have any more, so then the water table rises if we get more water molecules. Have a great day, guys. There is going to be a part 2 of this lecture, so tune in for that. Goodbye.